Greetings folks, welcome to this new video. In this video we're going to be talking about some of the data pre-processing steps that is required before you feed your data into a model. So basically we are going to include some of the feature engineerings and a bit of hypothesis testing, then outlier detection and many more things. I guess you gotta say that. Okay, so let's get into the video. So at first we are going to import our necessary libraries, obviously pandas and SNS for some visualizations, and matplotlib notebook, not in line. Okay, fine. So we have imported our data, and now let's see our data. Well, you can see our data contains age, sex, body mass index, and charges. What are these charges? Here, these charges are actually how much insurance charge you need to pay when you have some certain conditions, like your age is 18, sex is female, then how much charge is you going to pay, insurance charge actually. So our goal is to build a model where we are going to predict the charges for an individual, or an individual needs to pay depending upon some of the features like age, sex, body mass condition. So we are going to see how this charge respond on different conditions of body mass index, sex, age, how they differ, how charge differ with these parameters. Okay, so let's see at first sex and female counts, male and female count. So df dot sex dot value counts, yep. So male and female are pretty close, similar. Male is a bit higher. Okay, fine. Now let's do some visualization so that you can understand our data. Okay, now we are going to use sns.catplot. Okay, now here our x is going to be what? Age of an individual, and then y is our what? You can say our levels, maybe. Yeah, y is our charges, 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 and you need to specify the data is our diff. Okay, let's plot it. You can see that with age, charge is increasing, linearly increasing. At the first time it's linearly increasing, and there's three different distributions. So you can say that it's not just age on which charge is dependent, there's something else which is triggering the charges, and we'll see that. I'll see that later. Okay, let's see if sex, whether there's any difference in between different sex. So hue is equal 6. Let's see that. It's taking too much time. Not a big data set. Yeah. So yeah. Now you can see that male and female are pretty close. There's no much difference. Yeah. So yeah, we'll see that actually when we will do our hypothesis test. We'll see whether there's really huge difference, significant difference in between male and female. Well, now you can change the type of the plot. It's a scatter plot. Now we're going to see a different plot, kind of, well, let's say what, box plot. Box, yeah, let's do that. Oh no, what is this? Age versus charge, female. Oh, let's do some like sex here, and you. Sex charges. For the first time, forget about you. Yeah. Male and female, they don't have actually similar distribution. Both of them have some outliers. In the female, it's a bit more. And we'll see how we can detect outliers. Yeah, later. So female and male, here you can see male is going to pay a bit high charge than female. Yeah. Let's see if there's any interference of smoking status on this charge. So here hue is going to be our what smoke. Yes, smoker. Oh yeah, great difference. Now you can see when they are non-smoker, then both of the male and female have low charge. They are going to pay a low charge, and when they are smoker, yes, this color represents their smoker. So when they're smoker, both of them are going to really pay high charges. So smoking has really high impact on our charge. Yeah. So sex versus charge. Well, smoking. Yeah. Let's see if there's any difference on region by region. Okay. So sex charges data kind hue. What's region? Region. And no, it's not going to be a box plot. We're going to do bar plot. Yeah, so you can see southwest. Who is this yellow? Southwest. Yeah, in both cases, both sex groups, females and males, people who are living in the southwest side, they're paying high charges. Yep. And this northwest is going to pay low charges. Seems like they're racist. Or maybe not. Okay, we're going to see a bit more on region. df dot group by. We're going to group our data by region. Group by region, and we want our output on charges. So dot, let's say mean values. Let's see that. Oh no, df dot group by region charges. That's the problem. Group 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 by. Yep. Now you can see the values. You can sort it. Dot is what is sort values by what? By sorry, no by sort values ascending equal false. Yep. Now you can see. Yep. Southeast, isn't it? Yep. Southeast is going to pay high charge. So 14,000, 13, 12, 12. You can plot it also. Dot plot plot kind equal what? Bar. Yeah, comma quotation. And as we are using a notebook matplotlib, so you need to say plt dot figure. Okay. Yep. Now you can see that. No, that's not much difference. 2000, not 2000, 1000. Yeah. Well, let's see what body mass index and charge, which I think will have larger impact on charges. So SNS dot cat plot, or you can do LM plot. Now our X is going to be body mass index, so BMI and Y. And y is what? Y is charges, charges, charges. Now the data frame is df, and let's plot it. Yep. So now you can see clearly that body mass index and charges have really a relationship, but it's not a very good relationship. Lots of outliers, and majority of them are here in this region when the body mass index is 30, 35, 20, 25 to 35 in this region, majority of data, and all of them are with low charge value. Now let's say I wanna plot it for when the body mass index is just 30, greater than 30. Okay, so how can I do that? So let's say, well, before that, let's add hue, sex. Hue equals smoker, not sex. Smoker. Now you can see smoking has significant impact on body mass index versus charge relationship. When the sample, when the individual is a smoker, then you can see quite a good relationship. And for the non-smoker, it's not a good linear relationship. That's poor relationship. But when he's a smoker, or he or she is a smoker, then this is quite good linear relationship. Okay, fine. Let's see, we wanna plot it for when the body mass index is above 30. So how can I do that? We know how to filter our data, and now we are going to apply that method here. So data is not just df, we want data for what? When the body mass index BMI is greater than what? Body mass index is greater than 30, let's say. Okay, so we have filtered our data and now plot it. Now, one valuable insight that you can get from this plot is that body mass index doesn't have any good relationship with charges if he is not a smoker. Okay, now you can see that here, that if the subject is not a smoker, then body mass index and charge, they don't have any good correlation. But when he or she is a smoker, then there's a really good relationship, linear relationship. So yeah, that's I think a good plot. So now let's head over to hypothesis testing. Okay, hypothesis test. Okay, heading hypothesis. Well, now our first hypothesis is, let's say we want to know, do the charges paid by female significantly differ from the male. So here our null hypothesis is like they don't have any relation, they don't differ significantly. And while on the other hand, alternate hypothesis is, yes, they differ significantly. So there's a statistical significance. So to do that, at first you need to segregate our data. You need to make two new data frame. One is for female and another is for male. So now let's say female is equal to df.lc. Now what? df when sex is equal female. Okay, so let's see what it returns. At first doesn't, I'm not going to store it. So it's just going to return us the data set for female. You can see sex, female, but we don't want all the columns, sorry, we want just this charge column for females. So you can do that dot charges charges. Now you can see all the other columns are gone. The same thing you can do by, that's another way of doing that, a comma, then a quotation charges. Now you can see same thing, and now you're going to store it in female. Okay, so similarly you need to make another column for male, and for male you need to just change it to female to male. That's it. Now SciPy provides us pretty handy libraries to test our hypothesis. Okay, now we are going to import our SciPy library. From SciPy we are going to import t-test, and right now we are going to do a t-test. We can do t-test, z-test, ANOVA, many there's many tests, so that's actually another topic to discuss about. I'm just going to briefly talk about this t-test and maybe z-test also. So we have imported it. Now task is what, and then we are just now going to pass our two datas, male and female, and this t-test int function is going to figure out by its own other things. So male, female, and what, that's another argument. Equal var, that is variance. Do they have equal variance? No, they don't have equal variance. You can also inspect that. I'm just going to say QL equal var equal false. Fine. So let's see what it returns us. So it returns us a t statistic 2.18 and one p-value, and this p-value is less than 0.05, so we can reject our null hypothesis and accept our alternate hypothesis, that is they do differ significantly. So you can say that the charges paid by male do differ from female statistically significantly. Alright, now let's see one z-test, and that is actually, there's nothing to do with the charges column. It's now we are just, let's say we want to know, is there any difference or there statistically significant difference in between the proportion of smokers in different genders. Let's say, so what I mean is that I want to know, does the number of female smokers significantly differs from the number of male smokers in this data set. So at first we need to do what? We need to segregate our data as we did for the previous one. So here we need to know the number of females in our data set. So now you can see that value counts. You can see female 662, total number of female in our data set. So we want to grab that. How can I collect it? It's in the index number 1. Okay, now you can see just 662. Fine. So it's number of female. Now for the number of male, I need to do a little bit of change, 0. Yep, now you can see number of males. Sorry, yes, it's 676. Yeah. So now we want to know, from those 676 male samples, how many males are smoker. Alright, so how can I do that? It's like this, same previous one. Copy that, paste it, df.loc, and what, df.sex equal what, male, and we want our output on smoker dot values count. Just see what it returns. Yep, you can see yes or no. For males, yes is 159. So out of 600 and what, I don't know. So let's say out of 600 samples, 159 males are smoker, and so it's in the position of what, 1. Okay, let's see the same thing for female. How many females are smoker? 6 is female. Fe female, so it's 115. Well, now that we know the proportion of or number of males or female smoker, now it's time to run the proportion z-test. Fine, so to do that you need to import proportion z-test from stats model, and here what we are passing is number of males and females that are smoker. So here 115 female smoker, and this is male smoker, and here the total number of females and males respectively. Well, now we're going to run it. The values it's going to return is, one is z-test value and another is our p-value. So our p-value is less than 0.05, so we can reject our null hypothesis and accept alternate one. That is, yes, the proportion of male and female smoker do vary significantly, or statistically it's the result is significant. Fine, so I think that's all about hypothesis testing in this video. Maybe I'll make another video on that alone. So now we are going to talk about outliers. Outliers are actually some of the abnormal values in our data set, and there's a number of ways to detect outliers, and we're going to be talking about what quantile interquartile method. Okay, so at first you're going to see percentile, some percentiles. So what does 25th percentile, 75th percentile mean actually? So let's say df dot age dot quantile, sorry, QANTIL quantile, isn't it 25th? Yep. So the 25th quantile, that is 25th percentile, the age 25% of our samples age is below 27, and if you write here, let's say 0.75, that is 75th percentile, that means 75% of our samples age is less than 51. And now if we see this, we are going to look at this percentile using a box plot. Then I'm just going to import my box plot. Then box plot is, I'm recording it, box plot age. Now here you can see that, yep, 27, this is our 25th percentile, and or you can say quantile 1, and this is our 75th percentile, this upper one, or you can say quantile 3, q3. So here this is q3, and if you write what 25th percentile, then it's called quantile 1 in box plot q1, and the difference between them, that is what q3 minus q1, is known as interquartile range, IQR. So yep, interquartile range, yes. So in this graph you can see that, so that 51 minus 27 represents the interquartile range, and the way of detecting outlier is, Alright, now the values that goes 1.5 times interquartile range from this third quantile, or those values which goes below 1.5 times interquartile range from this first quantile, are known as outliers. So now the rule for that is just like that. So now you're going to actually set some limits, and one upper limit and one lower limit. And the upper limit is the values that goes 1.5 times the interquartile range. From what? From this third quantile. And for the lower limit, we're going to say just Q1 minus 1.5 multiplied by interquartile range. So this is our upper limit, and this is our lower limit. Okay, well, now it's time to print those outliers out. So to do that, we're just going to df in a bracket, square bracket, going to pass df dot age. We're going to extract those values less than our lower limit, and or not and, so that's why this pipe operator, and or df dot age greater than upper limit. So this will return us all the outliers for just this age column up. So we got no outlier in this age column. Now to make it a bit easier, so for all the columns, we are just now going to write one function here. So here everything is just as like before. So what you're doing, just writing a function, x is age, or now here you can specify x as any column name. Now outlier, outlier, let's say for which column now you want to see outliers. Let's say BMI. Number of outliers is 9, and these are the all outliers. Here for body mass index 49, 48, and if you would like to remove them, so just you need to just put what that symbol. You will see those values except outliers. Now we can also do that for our charge column, that is which is our our target column, and number of outliers. Here we got 139 outliers. Too much this is. So if now we delete all those 139 outliers for our charges column, it will also delete our some of the good rows from age column, sex column, body mass index column, because they don't have that much outliers. So deleting all those outliers is always not actually a good choice. So we can actually keep those 139 outliers. Alright, so far we have done what? We have done some of the visualizations to inspect our data, then we have done some hypothesis testing, and finally outliers. We saw how to detect outliers. Obviously there are some other ways to detect outliers. One is standard deviation way. Well, so far we have talked about hypothesis testing, data visualization, outliers detection, and now we are going to talk about correlation. And correlation analysis is really simple in Python. Actually, you just need to do df.corr correlation. Yep, and by default it's Pearson correlation, and you can change that also. Here you can see method is Pearson, so to change that you need to write method equal Kendall or Spearman, what you would like. Okay, one thing to notice here is that we got our sex column, region column, but those are not here because those are actually categorical categorical features, and as they are not they are not numbers, continuous numbers, in correlation you don't see them. So to do that, we need to convert them into dummy variables, and we'll see that in a minute actually. So let's make actually a heat map of this correlation. Fine, you can see now that children, no children, not highest correlation, higher 0.3 charge with age has high correlation. Now charge with BMI is 0.2 just correlation. Okay, let's see them later in more detail. Now this part is actually redundant, we don't need them. So to remove them, we are now going to just modify a bit. Now we are going to see core plot. Our data is div. Now you can see a beautiful plot, correlation plot in front of us, which is actually devoid of that redundant part. Well, now to see the correlations for all of the features, we need to convert our categorical features into dummy features, and before that I want to modify our features a bit, because as we saw in the earlier video that right in this plot we saw when body mass index is greater than 30, then they need to pay a high charge. And with that in mind, we're going to modify our data set a bit. So now what we're going to do is that we are writing a function when body mass index is greater than 30 and he or she is a smoker, then return fat smoker, and else everything is normal. It doesn't impact significantly the charge. Okay, now we are applying that function to our those two columns, body mass index and smoker, as you need to pass two columns. That's why this lambda function, and that this way. Okay, now yes, okay, fine. Now you can see one new column, fit fat. When the body mass index is less than 30, here 27, then it's normal. Okay, so everything is fine. Now we can run our own hot encoding or get our dummies. Now as this region is going to generate some of the dummy features, maybe 3 new features, I'm just going to drop it to avoid complexity. So df dot drop, you can keep it if you want, drop region one, and what in place equal true, so wouldn't have to reassign it to a new variable. In place true and x is equal 1. Okay, let's do that. Oh, in place, yep. Now let's see our data frame. Oh, we don't have any. What is that? Was that region? Now we're going to pass pd dot get dummies. Pd dot get dummies. You need to pass df our data frame and drop first. We are going to drop one redundant column from those dummies. Actually, yep. Let's see that what it returns. Sex, male, smoker, yes. If he's a smoker, then it's 1. If it's a non-smoker, then 0. If he's a male, then 1. If it's female, then 0. That's it. Pretty simple. And fit fat, if it's fat normal, then 1. And if abnormal, then 0. Okay. And we are now going to store it in a new variable df2. Okay, now we are going to run our correlation plot again. Core plot plot and our diff. Oh no, what is it? Diff 2. Okay, now you can see some changes and one high value here, 0.79. Charge with which smoker is, yes, that's pretty obvious. If he or she is a smoker, then he need to pay a high charge. And other thing is, yes, negative correlation. Yeah, fat normal, and what is it? I can see that. So okay, df correlation df 2.0 double. Yeah, now you can see charges. Well, I can also do one thing, charges. Yep, now every correlation you see here is with charge. So age and charge 0.299, that is zero point 0.3, moderate correlation you can say. But with smoker it got really high correlation, and fit fat normal, negative correlation. That means if he is abnormal, that is fat, then we'll get really high correlation. Yeah, if normal, then negative correlation, it's okay. The results we got from this modification seems to be pretty fascinating, but there's one more thing we need to test before we feed this data into our model, which is known as multi-collinearity. Right here you can see that when smoker is yes and fit fat normal, then they have pretty high correlation, and this is bad when you are going to use a regression model, because when independent features are correlated, the regression model doesn't work well. So for that there's a test known as variance inflation factor, and we're now going to see that. Alright, so here what you need to do is you need to import variance inflation factor class from stats model, and here just a bit of simple codes. Okay, let's run it, and we can see here our features and test score. And there's a rule of thumb that features with score values greater than 10 you can drop them, or better to drop. So you can see here fit fat normal and age. I don't think there's any problem in age, and BMI, body mass index, has higher score, so we can drop one of them. Well, now the question is which one to drop, and the answer is pretty reasonable, because we are going to keep that feature which has highest or comparatively higher correlation with our target variable. So right here you can see that fit fat normal has comparatively higher correlation with charges than the body mass index column, so definitely we'll keep fit fat normal. So but I'm not going to drop that right now, because that we'll see in our next video, how we are going to build our model and see if that has any impact on the accuracy of our model. And up next you'll see, I think, a lot more than that. So that's it for now. I hope I'll see you in my next video. Thank you for watching.